Alrighty, so now I did end up solving the problem. Let me try to put the thing here. The phi 1e cosine phi 2. Alrighty. So I found out yesterday that there's this thing called substitution, where z is equal to tangent phi 2. I believe it was cosine was equal to something. Let me see. Where did I put it? Now I have to find this thing. Yep, okay. So cosine sine x. And you have the 2c is equal to 1 plus c 2, and then cosine. Now I have 1 minus c 2, 1 plus c 2, and then the dx here. Dx equal to 2 1 plus c2 dz. So essentially, to solve this thing, you substitute that cosine for this guy here, and then the d theta is, imagine there's like a b there. Substitute that into here. That then allows, I'm not gonna do the whole computation here because it's like a lot. It's like several pages worth of deriving this thing out. For elliptic orbits that are, where is it? Where did I put it? Let me just say elliptic orbits whose energy is greater than 1. Where did I put it? Energy greater than 1. Here it is. So let me sort of write this thing down. And it happens to be that the integral, for let me start. So if I set the bounds here to angle 0, and then some angle phi. Okay, so angle, any angle, but the first angle is 0. Let's see, so let's put this e2 minus 1 squared 2, and then let me sort of e sine phi. The answer becomes this thing that I'm writing out. Let's see, 2 1 e cosine phi plus 2 e2 minus 1 3 to the power of 2, and then the arc R10 hyperbolic inverse tangent with the little thing there. I barely have any space. See if I could write, so square root of e plus 1 over energy minus 1 tangent phi over 2. And then this thing here becomes the answer for that integral. Yeah. So what does this thing do? Well, if you have a hyperbolic orbit, say, there you go. So this is a hyperbola. We're only analyzing a particle from here, say any point along the trajectory. This is some kind of nucleus, like an atom, and the alpha particle is being pushed that way, so it's repulsive, and it goes in this hyperbolic trajectory like that. Repulsive force. If I want to calculate the area underneath this particle's trajectory with respect to the central force, that is essentially what this formula gives you. This thing here, and the angle being the angle from the horizontal all the way up to the next sort of position of the particle. Yeah. Most interesting. Yep. There you go. That's it. It was like 12 pages, man. It was so many pages. I mean, you know, here it is. I mean, this is like all the work and stuff. But this, yeah. So if you ever encounter trigonometric integrals that are hard to integrate, you can use the Weierstrass substitution method, where you substitute, you know, your cosine, and then you make the d theta this thing, and then the integral then becomes a rational form. And mathematicians like basically figured those out. You can look them up.